We have Dr. Tony Colaprete. Tony's a NASA planetary scientist, and he leads the group, the flight instrumentation group. He's going to talk with us about Viper, the Volatiles Investigating Polar Exploration Rover. Tony.
Thanks for inviting me here to talk. This is an outstanding workshop. The breadth of presenters and amount of information covered is really impressive. I'll go quickly through a number of these slides because of the time limitations, but they'll hopefully be posted so you can see them, and this is recorded. I'm the project scientist for Viper. You've heard a few people mention it before. I'll give you a general overview of it and what it plans to do and the status of the project. Next slide. So as we've heard over the last couple decades, there's just been a revolution in our appreciation of water on the moon and other volatiles in general. We think there's everything from frost to potential blocks of ice to deep water, shallow, like Kevin was describing. I think there's a general appreciation too that just more observations are needed, in particular observations at the surface. And so this is where Viper comes in. Viper is the first, meant to be the first, not the final, the first step in that exploration, looking at water, trying to understand the origin of lunar water, but also understand how water could be a resource moving forward. To that, and we've really modeled the measurement plan and the techniques and processes after terrestrial resource exploration processes. USGS has been, and other mining companies have been doing this for many, many years and have developed an incredible set of processes, tools, et cetera, that we are borrowing, adapting really for the first time to off-world exploration. Right now, we are a confirmed mission with our critical design review this October, which has gotten here really fast, and we are set still holding schedule for launch in November 2023. Next slide. So Viper is all about understanding lunar water, and I don't want to spend a lot of time here because we've heard an excellent talk by Kevin on this topic, and everything we've learned over the last decade, including the observations from M-cubed superficial water, the L-cross results showing potentially a stratified layer of everything from 1% up to maybe 5 or even 10% water at depth. And we understand that there's this distribution both laterally and vertically now that is paramount to both exploration and science in terms of answering and addressing key questions about its origin and its general nature. Next slide. I think Kevin gave a really good synopsis of our understanding of water at the poles of the moon. And I've included this slide because I think we're still asking more questions than we have answers. So there isn't a good, solid understanding. There's a lot of contradictory observations. As Kevin pointed out, Mercury seems to behave itself. Where it's cold enough to have water, there appears to be water and lots of water. The moon just seems to be a bit of a more complex, less understood body at this point. So this is really why we need a series of missions to attack this on multiple fronts to really get at understanding some of these questions. Next slide. So the way Viper approaches this problem is with respect to exploration science. And so you may have seen this figure on the right here, the Lunar, which shows basically a generalized process from going from exploration of a resource to ultimately a proven reserve. I've highlighted in red the area where we are working in general, not just Viper, but everybody, in terms of understanding water and other volatiles on the moon in terms of resources. We've got definite information that shows that there is water there. It's indicated. We, in some instances, measured it, but we need much more information. Excuse me. And the critical observations that are needed are listed there on the left. First, we need to understand its distribution. We need to understand where it's located, both laterally and vertically. We need to understand its physical state. And this was mentioned a few times. Is it bound chemically? Is it ice in regolith? Is it blocky ice? How is it actually there? And then we importantly need to understand its context and correlation. And this is really important for understanding, well, how would we excavate it if it was there? How would we get at it? But also from a scientific perspective, understanding its context and correlation means we can understand the physical properties and characteristics of the environment that are controlling its distribution, its retention, its loss, etc. So these four aspects, these four points are critical to the Viper mission, and understanding the distribution, the physical state, the context, and the correlation. Next slide. So this is a bit of an eye chart. I'll go through it kind of at a high level here. These are is a brief summary of the Viper measurement requirements. The first is, again, determine the water distribution across what we call ice stability regions. The figure on the right shows a predicted ice stability depth. This comes from modeling that Dave Page and Matt Siegler have done with us, where they look at the depth at which temperatures are always cold enough for water ice to be stable. It doesn't mean water's there. It just means the temperatures are at least cold enough for it to be stable over long geologic periods of time. The white areas in this the upper figure are where water ice is stable at the surface. These are the permanently shadowed cold traps. What you can see is the range of colors around the white area indicate the depth at which you would need to go to find temperatures cold enough to hold on to water. And this is really interesting finding, is that it can be outside of permanent shadowed regions and quite near the surface. The red areas, for example, are within the top 10 to 20 centimeters of the surface. Temperatures are always cold enough to hold water. We've, on the project to organize this in terms of a mapping process, have defined these areas as ice stability regions and divided them into four categories. And that's what shows in the bottom figure there. Surface, so that's PSR cold traps. Water is expected to be stable at the surface. Shallow, it's in the top 50 centimeters. It's expected to be stable. Deep, bottom 50 centimeters. And dry, we do not expect temperatures to be always cold enough to hold water down to the depth of more than 1 meter. And so this allows us to actually categorize, plan, and put together a mission around identifying and characterizing these ice stability regions. The other important and an important aspect here is covering enough area to do this. This Viper really is a reconnaissance mapping mission. It's not going to one of these sites and making a measurement. It has specific requirements for overall area density and coverage. And again, this gets back to the resource mapping techniques we use on Earth. We'd be using advanced geospatial interpolation techniques like kriging to actually get at better estimates of the overall water ice content in regolith. So we have to cover a significant area, not just make point measurements. We need to measure down to at least 0.5% weight water. We do much better than that. Also importantly, for science, we measure key isotopes, which will help us to understand the origin. We have to also cover large scales. There's expected to be quite a bit of heterogeneity, especially in the top meter. So we need to measure scales from decimeters all the way to kilometers. And we have to measure subsurface. We need to profile the water ice or volatile concentration as a function of depth. Next slide. This is a quick overview of the Viper surface segment, the rover. It is rather boxy, but that's because it has solar panels basically all around its sides. It's the sun's never above about 5 to 6 degrees above the horizon to the poles, so it's always coming in right above the horizon. I won't run through all these. You can read for yourself. But most importantly, it is a solar-powered rover. It's not nuclear. and it uses direct-to-earth communications. So it's not relying on a relay satellite at all. Those are key in terms of determining where and when it can go on the lunar surface. Let's go to the next slide where I talk a little. This shows just basically how it fares against other rovers in terms of size and volume. Next slide. Yeah, this is the instrument overview. I think probably most interesting to this group. It has 4 primary instruments on it. The ones across the top are on continuously while roving and drilling. We never turn them off in a nominal scenario. And that's really important, again, to get this total coverage that we need. We need to absolutely have total coverage. So the rover's been designed to be to accommodate this requirement. On the left is a neutron spectrometer. It's out in front of the rover, and it's measuring hydrogen down to a meter's depth continuously as we're going. The one in the middle is a mass spectrometer, M-SOLO. It measures, again, while driving, gases coming up from the surface, and also while drilling, characterizing cuttings. The instrument on the far right, NERVIS, is a combination of a near-infrared spectrometer, a thermal radiometer, and a multicolor imaging system that's characterizing the surface composition, frosts and ices, etc. And then finally, lower left is the Trident drill. It's a 1 meter percussive auger drill that will sample in 10 centimeter bites down to the surface so we can profile water content with depth. Next slide. This is a cartoon of the Viper mission phases. As you heard from Zach, the CLPS office is delivering the lander or the rover to the surface with a CLPS lander. And so you see in the far left there, that first part, the lunar transfer, lunar orbit, and landing, that's not our mission. That is the Astrobotic mission who provides the lander. This is, again, part of the really exciting new paradigm of CLPS. Once we land, then it becomes the Viper mission. And you can see you have this green bar called surface operations. We're looking at about 100, maybe more days on the lunar surface. And it's broken up into these various legs. You can see in the yellow there. Because we're direct to Earth communication, we have to get into what we call a hibernation state, or really it's a safe haven state as we call it, where the Earth sets below horizon and we can no longer communicate and rove. We're not autonomous, we're semi-autonomous. So anytime we're out of comm, the rover parks. What that means is every about 14 days or so, we find an area that's nice and sunny. I'll talk about this more in a bit, and park. And wait for the Earth to come back up, and then we continue the mission. Next slide. I mentioned, or it's been mentioned a few times, the Griffin lander. This is Astrobotic Technology is delivering the Viper rover on this lander. This is a cartoon, or artist conception of what that will look like. Next slide. So we have 2 primary modes of operation I've touched on already a little bit. One we call prospecting, and that really means we're driving and measuring continuously while we're driving. This is a cartoon that basically summarizes what we're doing while we're driving. As I mentioned, we have the neutron spectrometer, the near-infrared spectrometer system, and this mass spectrometer, M-SOLO, on continuously while driving. As you see in the cartoon there, as we go along, we can track neutron count rate, which is directly a function of the amount of hydrogen and how deeply the hydrogen's buried. We can measure surface temperature, gases coming off, surface frost. We'll be able to do these all simultaneously and be able to correlate all these things together, which again is really important to help us better understand the processes controlling the distribution of the volatiles. Yeah, next slide. And then we have drilling, so prospecting and drilling. And the drilling we call subsurface assays. And what happens there is we park and we begin to drill. While drilling, what we do is we come down in 10 centimeter bites, we bring up a sample of 10 centimeters in length, brush it onto the surface, and that forms a cuttings pile. The M-SOLO mass spectrometer and the NERVIS near-infrared spectrometer are looking at that continuously. We've demonstrated this in testing many times, I think about 4 or 5 times at Glenn over the years. And it's a really easy, relatively easy, simple technique to characterize quite well how much water is actually in the subsurface. So each 10 centimeter bite, we image it as well to understand what's coming up and the forming of the pile, et cetera. But why this is important, not just to get that vertical profile for itself, but the neutron spectrometer can use actually those vertical profiles to better constrain the modeling as to what the burial depth is. The neutron spectrometer measures both epithermal and thermal neutrons. If they have a way to better understand the depth of the desiccated layer, they can actually get a much more accurate prediction of the total hydrogen content and burial depth along the entire along the entire traverse. So it's just like we do in terrestrial prospecting or exploration. You have a lot of denser data sets, and then you have diffuse data sets drilling to help you understand that dense data set. Okay, next slide. Where are we going? Well, we've been studying a lot of places, both North and South Pole. We are definitely going to the South Pole. And we've looked at 3 primary locations. These are governed by, one, where we see a significant amount of hydrogen. 2, there's a variety of thermal environments. We need to be able to visit all the ice stability regions I mentioned earlier. We can't just visit 1 or 2. We want a variety of them. 3, we need the periods of shadow when the Earth goes down to be relatively short. We're solar powered and battery powered. So when the sun goes down, we rely on our batteries to stay warm. And the yellow squares here show periods of areas where we have less than 90 hours of shadow. We call these safe haven areas. I've outlined 3 areas there, the Nobile, Shoemaker, and Haworth sites. These are areas that we've looked into with great detail, trying to understand the characteristics of the site and whether or not they meet the mission requirements, as well as they meet the rover performance requirements. Next slide, I think, gives an example of a traverse. Oh, at each of these sites, sorry, we have to do a lot of dynamic traverse planning. Because we're solar power and direct to Earth, we have to constantly, excuse me, be in sunlight and in calm, unless we go to shadow ops, which we do when we go into a PSR. And so we have to look at dynamic maps, static maps like slopes, and reconcile them all in our traverse planning and landing site analysis. Next slide. So this is an example of a traverse in the Nobile area. Unfortunately, I can't play the movie here. It would be a movie. You'd see those green, the figure to the right shows a number of concentric green circles. The largest ones are 1 kilometer apart. You see a darker green line that's drawn across it between the areas of red and yellow and green. That's the modeled rover traverse. This particular traverse visits all 3 of those PSRs. The largest one to the top center is about 500 meters across, so it's fairly large. This is a 106-day mission that we've modeled here, with actually there's 28 more days unplanned at the end. And you can see some of the statistics there. It covers more than 26 miles, or sorry, kilometers, 27.4 kilometers. And it has what we call 12 science stations. Basically, in each of those ISR types, PSR, shallow, deep, and dry, we have a science station where we do mapping of the area. One thing I'll point out is that Kevin mentioned that we had a 0.005 or something kilometers squared. Actually, in the PSRs in this traverse, we have about 1.2 kilometers of mapped area in PSR. So we will be actually covering quite a bit of area in terms of mapping capability. Next slide. I think I'm getting towards the end. Yes, thanks. So we've got this fascinating, complicated story about lunar water, and there's going to be a number of assets, not just Viper, brought to bear on these new questions. And this is really an incredible, exciting time for all of us, leading into Artemis and beyond. Viper will conduct exploration science, addressing both fundamental science question as well as exploration science critical to ISRU architectures. And it, as such, it really is a cornerstone for a great number of communities in terms of taking the first steps to understanding the distribution and origin of lunar water. With that, I think that's it. Thank you. Next slide, I think, is a thank you slide with a pretty picture. Yeah.
Great. Thank you very much, Tony. I think we have time for a couple of questions here. Tony, what is your opinion of AMBI active neutron probes for moisture detection?
Radioactive moisture probes. I don't know not much about them, so I don't think I have I could share an opinion. I'm sorry.
Not a problem. Very interesting. And let's see. These are mostly comments in here, actually a number of comments. So if you
Good, I'll read
wouldn't
through them.
mind, please looking through the chat. I think they're turning into quite the conversation. So thank you very much for sharing that update on Viper. We're really looking forward to seeing that land.